Antihydrogen is the antimatter counterpart of hydrogen. Whereas the common hydrogen atom is composed of an electron and proton, the antihydrogen atom is made up of a positron and antiproton. Antihydrogen has been produced artificially in particle accelerators, albeit at energies too high for detailed study. CERN experiments created low-energy antimatter in trapped atoms for precision studies. Scientists hope studying antihydrogen may shed light on the baryon asymmetry problem, or why there is more matter than antimatter in the universe. The standard symbol for antihydrogen is H. Experimental history. Accelerators detected hot antihydrogen in the 1990s. Athena studied cold H in 2002. It was first trapped by the antihydrogen laser physics apparatus team at CERN in 2010, who then measured the structure and other important properties. Alpha, Aegis, and GBAR plan to further cool and study H atoms. Characteristics. The CPT theorem of particle physics predicts antihydrogen atoms have many of the characteristics regular hydrogen has, i.e., the same mass, magnetic moment, and atomic state transition frequencies. For example, excited antihydrogen atoms are expected to glow the same color as regular hydrogen. Antihydrogen atoms should be attracted to other matter or antimatter gravitationally with a force of the same magnitude that ordinary hydrogen atoms experience. This would not be true if antimatter has negative gravitational mass, which is considered highly unlikely, though not yet empirically disproven. When antihydrogen comes into contact with ordinary matter, its constituents quickly annihilate. The positron annihilates with an electron to gamma rays. The antiproton, on the other hand, is made up of antiquarks that combine with quarks in either neutrons or protons, resulting in high-energy pions that quickly decay into muons, neutrinos, positrons, and electrons. If antihydrogen atoms were suspended in a perfect vacuum, they should survive indefinitely. As an anti-element, it is expected to have exactly the same properties as hydrogen. For example, antihydrogen would be a gas under standard conditions and combine with antioxygen to form antiwater, H2O. Production. In 1995, the first antihydrogen was produced by a team led by Walter O. Allott at CERN. In the LIA, antiprotons from an accelerator were shot at xenon clusters, producing electron-positron pairs. Antiprotons can capture positrons with probability about 69819999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999Fermilab measured a somewhat different cross-section, in agreement with QED predictions. Both resulted in highly energetic, or hot, antiatoms, unsuitable for detailed study. Subsequently, CERN built the antiproton decelerator to support efforts towards low-energy antihydrogen, for tests of fundamental symmetries. The AD will supply several CERN groups. CERN expects their facilities will be capable of producing 10 million antiprotons per minute. Low-energy antihydrogen experiments by the ATRAP and Athena collaborations at CERN brought together positrons and antiprotons in penning traps, resulting in synthesis at a typical rate of 100 antihydrogen atoms per second. Antihydrogen was first produced by Athena in 2002, and then by ATRAP, and by 2004, millions of antihydrogen atoms were made. The atoms synthesized had a relatively high temperature, and would hit the walls of the experimental apparatus as a consequence and annihilate. Most precision tests require long observation times. Alpha, a successor of the Athena collaboration, was formed to stably trap antihydrogen. While electrically neutral, its spin magnetic moments interact with an inhomogeneous magnetic field. Some atoms will be attracted to a magnetic minimum, created by a combination of mirror and multipole fields. In November 2010, the Alpha collaboration announced that they had trapped 38 antihydrogen atoms for a sixth of a second. the first confinement of neutral antimatter. In June 2011, trapped 309 antihydrogen atoms, up to 3 simultaneously, for up to 1000 seconds. They then studied its hyperfine structure, gravity effects, and charge. Alpha will continue measurements along with experiments EGIS and GBAR. Larger antimatter atoms such as antideuterium, antitritium, and antihelium are much more difficult to produce. Antideuterium, antihelium-3 and antihelium-4 nuclei have been produced with such very high velocities that synthesis of their corresponding atoms poses several technical hurdles.